Okay, hello everyone. Okay, today we continue within the topic of the tree. Since we come back from the midterm break, it's been a while. Let's quickly review what we have been learned in the last lecture. So last lectures we learned about for the tree for insertion function. So it's how to insert a node into a tree. To identify the parent node under which the new node should be inserted. Second step will be inserted in the new node as a child of the parent node. The strategy is to traverse the tree to find the target parent and then to insert the new node as a child of that node. Let's have an example here though. Okay, look at this tree. For example, we want to add insert this node under node 6. If we apply the what? For the pre-order traversal. So for the pre-order traversal, what are we going to do here? So we'll traverse the tree based on the order of the 1, 2, 3, 5, 6. Oh, now we find what? The node 6, and then we're going to insert the new node 7 under what? Node 6. Okay, so here's a code regarding for the this type of insertion function. We can look at here though, it's the structure of the tree node. We are being seen many times. And then this is for the pre-order logic, pre-order traversal logic. Okay, so this is we recalled on the previous lectures regarding for pre-order traversal. So based on the pre-order traversal logic, we modified for insertion function by the pre-order traversal. As we can see here though, this will use a recursion, right, to process the pre-order traversal. On this type of insertion function, what we just need to modify the which part? Okay, to once the recursal part pretty much similar, right? Compare within the pre-order. We only add this piece to find and insert. Okay, to find and insert, and then to stop the further recursion. Okay, that's it. Okay, now can we use in the post-order traversal? Okay, let's recall the post-order traversal logic. Okay, so the post-order, what do we do here though? We have this using the recursion function, right? To visit the child and to visit all the children, and then process the parent node. Okay, so process the node after children. So this is for post-order traversal. But there's some unnecessary recursion call if we apply the post-order traversal into the insertion function. So this will be cause less efficiency. It works, but compared with the pre-order traversal, post-order traversal is not recommended. So I have a question here though. If there are duplicate nodes, how to insert? Okay, for example, we have this scenario. So for under 3, for both children node, they're all the same, right? A duplicate, both are 5. Option 1, we insert under the first match. Okay, so here's a code regarding for insert on the first match. It means to once you find the first target node, we just directly insert. All right. Okay, so we modified this piece. Okay. Okay, same scenario. Option 2, we insert under all matched nodes. So we keep going to even after one match. So we'll continue to insert a new node as a child of every node within the target value. Okay, here's the code. So once we find the target, okay, so we're going to insert. Okay. Option 3, what do we do here? We're using the unique node identifier instead of the value. So this means we assign each of the node have the sort of the ID. Okay, so we add the unique identifier for the tree node structure. So what to do here though, one way to declare the node, we add the ID for the corresponding node, and then we just pass what to pass over the target ID, and we know which target we're going to insert with. Okay, here's the code. You guys can review it after. Okay, for deletion function. So for deletion, there's a first type of deletion is what? To delay the entire subtree, right? So it means delay the node n and also delete all his children. For example, for the same example here, if you want to delay the node 3, in this scenario, what do we do here though? Delay the entire, okay, delete the entire subtree of the node 3 and become this new node after process deletion. Okay, how this delay works here though? Okay, so now we find what? 5, we delay from 5 and then delay the children 6, and then we can delay the node 3. So what do we use here? We use the post-order traversal for this scenario. Okay. So we leverage the post-order traversal, we process the delay subtree. We can conclude the delay subtree function by the recursion. Okay. Okay, second scenario is regarding for deletion, is for what? Delay the node and also promote its children. So the strategy is you must find the node first, okay, so which means the parent node match, and then you remove that node and retouch all the children to its parent. Okay, let's make an example. Same tree we saw many times already. For example, we delay the same thing, delay the node 3, and then what we do here in this scenario will become what? Become like this. Okay, so the node 3 being delayed will be retouch its children into the node 3's parent, which means node 1, and then we can see the result of the new tree after delay the node 3. Okay, so it means we touch the node 3 children, 5 and 6 retouch into the node 1. Okay, how that works here though? Let's look at the step by step. Okay, so we first to find the node, okay, and then we're going to remove these children, right? We're going to remove the node and retouch the children to their parents. For the logic we applied is for what? First we need to link into the 1 from the 5 into their grandparents 1, okay, and both also apply for node 6 in link up into the grandparent, right? 1, and then we're able to delink between 1 and 3, and then to remove node 3. That's how the logic works. Okay, so in this case, as we can see, we use a pre-order traversal to process this kind of deletion. Okay, here's the code. Okay, you guys are going to review it. Okay, review it after. Okay, so this code is for delay the node and promote his children. And then we have the leave only deletion. So you can only delay a node if it is a leaf. That says this node, leave node, it's there's no children. Okay, so there's if you check the leaf, it means this node have no children. Also, the strategy we're going to apply is to traverse the tree to find the target node, and then to check if they have the children. If they have the children, reject the deletion. If they have no children, remove it from its parent-child list. Okay, for example, same tree. What a leaf node? We have the 2, 5, 6, 4 because they don't have children. Okay, so in this case, we're using what? For pre-order traversal to process the deletion. Okay, here's a function you guys can review after. Okay, soft deletion. This has been technique being used in the many places, right? So also using the database design, right? So soft deletion is not a real delayed. It's what we just have the flagging the node. It's add the Boolean variable here if delay is delayed to define it true or false. Okay, so if you found this node, you find you will add the you define this is delayed, the variable is true, otherwise it's keep false. So it means the node is still there, it's just not showing to the user. Okay, again, this is not a real delayed, just hidden, right? And you can make the recovery if you need. For example, we have this tree. Okay, we soft delay node 3. Okay, what do we do here? We also need to soft delay his children, right? 5, and soft delay his children 6. It means, so if we, for example, to traverse this tree, 3, 5, 6 won't be shown. In this scenario, we're going to be using the pre-order traversal for the soft deletion. Okay. Here's the code. We modify the tree node structure of the tree node. The Boolean variable is delayed. Okay, so default is false. If you want to delay it, you change it to is delayed Boolean variable into true. Okay, so they won't be showed up to the user. So also you need to modify to display or corresponding functions to check, pre-check this true or false to determine whether you delay this node or not. Okay, here we go. It's regarding for the code. You guys review afterward. Okay, so as I said, okay, so you make a soft deletion. Regarding for print tree, you also need the precondition to check this node is being delayed or not. All right, okay, let's jump into today's topic. It's regarding for search to search in a tree. First, what's the purpose of the search in the trees? Okay, here's some scenario will be implied for the search. First, check if a value exists or not. So as we learned regarding for deletion, right? Deletion also insertion. So we want to what? We want to check this value exists or not. Okay, so this part we need using the search. Second scenario will be find a node to retrieval or to modify its data. Okay. The third is using in the routing, decision making, and game tree. Also the XML parsing and all other kind of scenario. It's based on using the structure as a tree structures. This is being used in many places in our daily life. Also, it's the basis for the advanced algorithm like minimax and tree lookups and so on. Okay. That's why the searching in the tree is very important logic. Okay, in the context of the general trees, there are two core fundamental search strategy. First, we call the breadth first search, also called the BFS. Second, we call the depth first search. It's also, we call them DFS. Okay, so these two are the most important and fundamental searching strategy in the tree. These two types of search both belong to the non-informed search. Also, we can call the blind search. So for non-informed search, so they have the what? They have no knowledge of how far the goal is, or the how desirable the node is. Okay. Second, it only knows the structure of the tree and not how to spend the node. The third is it doesn't use any domain-specific heuristic to guide the search. In the opposite, they also have other search. They give what? Give the heuristic, okay? Give something the priority. So this type of search will not talk about in this lecture. Okay, for today's, we'll mainly focus on the non-informed search for the breadth first search and depth first search. Okay, let's discuss about the breadth first search. Breadth first search to explore is a level by level. It means to visiting all the nodes at one depth before going deeper. What they do here though, they're doing what? Root node expanded first, and their root children expanded next. So it's all the roots, all the nodes at the given depth are expanded before any node in the next level. Okay, let's look at this tree again. If we process the breadth first search, how this work? So what we do here, we starting from the root node 1, and then they have what? Children. What the children of the node 1? Have a 2, 3, and 4. And then we're going to expand. It's a children node for 2, 3, and 4. So these children of the node 1 to expanded, because there's only have 2, 3, 4 children, right? There's no more. And then what we're going to here though, we're going to look at it's node 2 and his children. Because node 2 have no children, and then we visit back to node 3. And node 3, they have 5 and 6, right? The children 5 and 6. And then you have to put in 5, visit 5 and 6. Okay, the children of the node 3 being complete, they only have 5 and 6. And then, that's it. So it means level by level, okay? First, the root level, and then these children, 2, 3, 4, and then they come back into the third level, 5 and 6. So the breadth first search visits the nodes in the order they discovered. So what type of these structures you can think to apply for breadth first search? So this looks like the word. It is a first in, okay, first in, first out. For example, we look at the node 1 and then pop out to search in their children 2, 3, 4, and then we look at node 2, right, and then their children, and accordingly look at the node 3 and his children 5, 6, right, and then look at node 4 and his children. This applies for what? For the first in and the first out. What data structure we learned, I mean the linear data structure we learned for first in, first out principle is what? It's a queue. Yes, it's a queue. Okay, so we need to using the queue to apply the breadth first search into the tree. Okay, let's look at code. You guys can pause here to review the code. And okay, so but we continue from here. Okay. All right. As we can see here, though, we have the tree node structure been seen many times. Okay, we have the value, have the vector, right? Vector of the node. This is the code regarding for breadth first search. Okay, let's go through this code. So let's check whether root it's empty or not. If a root is non-pointer or is empty, we're going to do nothing for return. Otherwise, what we're going to do here, we declare as a queue. Okay, declare as a queue. We're going to put the root into the queue. If this is a pre-check, the queue is not empty. What we do here, we want to find what? The first elements of the queue. Okay, we use the queue dot front to get the first of the elements. We can define the current, and then we do the pump up. Okay, we do the pump up. So it means the first elements we're going to pump out. And then we're going to check all their children about this current node. Okay, so if we find their children, going to push into a queue. That's the logic for the breadth first search. Okay, let's look at more details regarding for this logic. Okay, so we have the tree, this tree. Okay, same tree. We declare as a queue. Okay, what do we do here? The first step, going to put node 1 into the queue, right? Node 1 put into the queue. So we're going to come to the while loop. So the queue is not empty, of course it's not empty. And then we have a current, okay, current node point to where? Into node 1. And then we do the pump up. So it means what? Node 1 will be pump up, okay, pump up. And it's going to be what? To display it here, display the value here. Let's check the node 1 for all their children, right? Oh, they find what? How many children? 2, 3, 4. Okay, so we're going to in orderly put the children into the queue. Okay, so 2 push in, 3 we push in, 4 push in into the queue. So the order we can see here is the same order of their in order on the tree, right? From left to right. So it's from left to right in the queue, okay? And one next step here. Come back into the while loop to check queue is empty or not. So now in this case, queue is not empty. So what we can for the current and what we look at next is what define the current node equal to queue front, which means 2. Okay, and queue pump up the pump up will be pump up the element of 2 to display it here, okay? And then we're going to try to push the children of the node 2 into the queue. And we can see there's no children for node 2. And then this loop will be what? Will step out. We continue with the for loop. We come to where in node 3 now, right? So the current will be equal to the Q front, which is in node 3. And then we have the pump up of the node 3, because the node 3 now is the first element of the queue. And then we have to display the node 3. And then whether we're going to push all the children into the queue of the node 3. Node 3 have how many children for node 3? We have 5 and 6, right? And then we'll be push the children of the node 3 into the queue, 5 and 6, which from where? Left to right, from left to right, which means they keep the same order. All right, okay, so this node 3, their children complete pushed, going to continue with the while loop. So the queue is still not empty, right? So what we do here, to current will be defined as a queue front, it's node 4. And then we do the queue dot pump up. So node 4 being pumped up and displayed, okay, displayed here. Okay, now let's check for node 4 whether they have children or not. Looks like they don't have children. Yeah, so this for loop won't be applied for node 4. And then we continue within the while loop. Okay, so while loop, it's still not empty. And then we define the current node into the where? Q.front. What's the Q.front? It is the element, right? This element, right? It's node 5. Okay. So current is node 5. We do what? Do the pump. Okay, pump the node 5. Go to pump. As displayed here. Then we check for node 5 have a children or not, right? But node 5, there's no children for node 5, so we want to apply this for loop. We keep going, okay? Keep going for while loop. We find node 6, which is in the front of the queue. So current, we define the node 6, going to point to node 6, right? And next, going to pump up the node 6 to display it here. And we're going to try to push the children of node 6, right? But node 6, there's no children, right? And then this for loop is not applied for node 6. Now we come back in the while loop. Oh, we can see our queue now is what? It is empty. So this breadth first search is being complete. Okay, this is how the breadth first search works. As we can see, this is what print. So the order is 1, and then for first level, right, root level, and then the second level 2, 3, 4, and then to visit the what, third level 5 and 6. So we're using the queue to implement the breadth first search. Okay, now let's discuss about the time complexity regarding for breadth first search. So here the type of complexity we discussed regarding for breadth first search is in the tree. So as we can see on the code here, each of a node has to be visited, right? Has to be visited what? Once on the tree. So this type of complexity is what? It will be big O of n. So the reason we just said each of the node is visited what? Exactly once. What about the space complexity? So the space complexity means how many memory space being used. What are the maximum memory space being used? It's big O of W in average case. What's a W here? W is a maximum number of nodes at any level. Okay. In this scenario, we can see here it's what's the maximum number of the weights. Is the second way, right? Second. Okay, 2, 3, 4. So it means what the maximum number being spaced in the queue. As we can see here, maximum number we use. We can see how many space being used in the queue. Entire process maximum is what? It's 3. Okay. So for the space complexity, what's the worst scenario we can think? Yeah, okay, we just saw that example, right? From the queue. Okay, so the worst scenario is what? You may store all the nodes at the widest level in the queue at once. For example, you have only one node, all their children is on the same level. Okay, it's a worst case. So it means on the queue, they have to what? They need at least big O of n, right? Big O of n space to support the entire tree. All right, okay. This is about the breadth first search. Okay, you may pause here to think and review what we just discussed about breadth first search. Now, next we discuss about we're going to discuss about the depth first search. Okay. For depth first search, also we call the DFS. Here's the definition of the depth first search. So the depth first search to explore as depths as possible along the branch before the backtracking. So the strategy is to expand to the deepest node, which means the search goes into the deepest level of the tree until a leaf node. If a leaf node is reached, the search will back up onto the previous depths. Okay, let's give example. This same tree, let's look at how the depth first search work. We want to go where? Go to deepest level first, right? We start from the node 1, and then we want to go to a deepest level, okay? For first visitor is what? It's 2, right? 2 so far, it have no children. In this level for 2 is the deepest. And then they back to the purest level and they can find where? Depths, the node 3, okay, for its children. Node 3. Find node 3 and they can continue with the deeper level, right? Because node 3 have the children 5 and 6. And then they're going to go to the deeper level for 5. And then the same level, they have what? 6, right? Okay, and there's no more deeper level for 5 and 6. They're going to come back, visit node 4. Okay, so this is how the depth first search work. As we can see for this order, we can recall what type of traversal we see before. Yes, we can see it's the same as a pre-order traversal. Okay, So the depth first search, it's the same as is a pre-order traversal. We already discussed about pre-order traversal to implement by what? By the stack. Okay, by stack. Because they go within the first in, last out, or last in, first out. It's a principle. So it's apply. This is this node visit. Okay. So the depth first search is implemented by what? By stack. Okay, let's look at the code. Again, this is a structure of the tree node. Okay, so have a value, have the vector of the nodes for their children. Okay, so this is a code for depth first search. What they do here, they first to check whether node is going to the node root is empty or not, right? Or is non-pointer. If yes, we'll do nothing. Otherwise, it's going to declare as a stack. Okay, declare as stack. We push the root node into a stack. Process the while loop to first check the stack is empty or not. If not, going to what? Going to the put the current node to the top node, okay, in the stack, and also for the pump up of the top node, and then to push the children in a reverse order so we can keep what? Left to right principle. So this code is exact same as what? Pre-order traversal. Okay, pre-order traversal. All right, let's go through this code again. Okay, go through this code again because we went through the pre-order traversal before, but let's go again. It's also part of to recall the knowledge. Okay, see how the depth first search works by using stack. Okay, let's declare the stack. So first we push the root into the stack. Okay, we go in the while loop, right? So the stack is of course not empty because have the root node, and we're going to do what? Define the current pointer pointing to the top node, which is node 1, because it's only have one node on the stack. And then we do the pump is disappeared, and going to display it here. Then we're going to push the children, okay, in the reverse order. So the order, because reversed, is going to be 4, 3, 2. Okay, from the right to left. Okay, from right to left. So we keep going for the while loop. Now the current going to point to the top. What's the top now? Node 2, right? Okay, node 2. Yeah, so the current is on the node 2. So we do and then we do the pump. The node 2 is pumped and displayed here. So current is node 2. We want to check or visit or push into children of node 2. But there's no children for node 2, so this for loop will now apply for node 2. And then next, what we're going to here is going to the while loop, right? We continue with the while loop, and we can declare the current node pointing to the top. So far, the top is node 3. Okay, so current will point to the node 3. Now for the stack, going to pump up of the node 3, and then to display here. And then we find and then we're going to find the children of the node 3, okay, in the reverse order. As we can see, to push the node of the children of node 3, 5, 6 in the reverse order into a stack will be 6 and 5. Okay, they'll be pushed into a stack. So it's now the stack in this scenario, right? We have 5, 6, and 4. We continue with a while loop. So current going to point to the top, which is what, 5, and then we do the pump, 5 being pumped and displayed here. 5, there's no children, so the for loop now apply for 5, and then we apply for what? Go with what? Go with the 6 at the top, right? And then pump up and displayed here. The last one is node 4. We're doing the pump up and displayed here. Same for there's no children for 4, so the for loop is now applied for node 4, and then the breadth first search is complete. All right, okay. So that's how the breadth first search works by the stack. Okay, so let's compare within this two search strategy, breadth first search, also the depth first search. Okay, breadth first search. This is breadth first search, the depth first search. Okay, so as we can see, the literally is just these differences. One using the queue, one using the stack. Some students may notice, okay, this is a different. Yeah, this is a different. But for depth first search, if you ignore from left to right, you can use the same code, okay, for the from the breadth first search first piece to push all the children into the stack. Okay, so it means will not follow the left to right. It becomes the right to left, okay, process. But the key things we can see that breadth first search and depth first search literally just we using the two different kind of the data structure. One is a queue, one stack. Okay. As we know, for depth first search, we're leveraging with what? Pre-order traversal. So pre-order traversal, we also have the way for using by the recursive. Of course, so depth first search also apply for recursively. So this is the code for depth first search recursively way to implement. Okay, same as a pre-order traversal. Okay, we have the precondition to check. If it's empty, if non-pointer, we just return nothing, and then to display, to visit all the node, and then to visit what? To children recursively. Okay, that's all about today's lectures. Thank you, everyone. Okay, we'll see you next time.